Yeah, so I'll be talking about ABCD pyhf. So it's this package that I wrote implementing this ABCD method for use in particular in my Atlas analysis, and then I published it basically as a repository on GitHub and on PyPy, so that hopefully other people can use it. So just as some background, so in my exotics Atlas analysis world, we're mostly looking for new physics processes that haven't been seen before, and we're looking for very rare processes, so very small amounts of both background and signal if the signal is there. So very, very few events, very hard to simulate these very rare background events. It's often like QCD multi-jet, just very rare QCD multi-jet events. So we can't rely on monocolor simulation for all our background. So we have pretty much always data-driven background estimations in order to search for signal on top of this background. And so the ABCD method is probably the most popular method for data-driven background estimation, certainly within Atlas. So this notebook just kind of goes through a toy example of this. So I just have some generated data that's just basically like toys of signal and background to try to just give an example of how this method works. So these data, fake data events and signal events were just generated in this other notebook in this repository. And so if I load these, so just to show what these events look like. Just double check here.
You can check your kernel, see if you're actually having the same issue that I had this morning.
Right. Oh, I see. The notebook just got killed. Yeah, sorry about that. Okay, yeah, just my local process got killed. There we go. Yeah, so this is the distribution of these kind of like toy signal events that I have here. So this is just a plane in two different variables. So the ABC method relies on finding two uncorrelated variables, observables from the data that you can see. And so here, these are just examples. So I call them X and Y. These are just some observable quantities from the data that you get from these events. So this is what the generated monocolor looks like. So it has some peak, and some standard deviation in both of these dimensions. But the important thing is that that these are uncorrelated in background. It doesn't have to be uncorrelated in signal. In this case, it is, but it just we want to make sure that we have some observable that we can use to discriminate signal versus background. And so, as you have in a real analysis, so you have a high statistics Monte Carlo signal sample where we can really understand where the signal is, but we won't have these statistics in the actual data. So the data might look something more like this, where I just switched to a scatter plot. So they're just individual points, and so the signal would be sitting somewhere in the middle here, but it's on top of this background distribution. So how do we know if there are real signal events here or not? In order to do that, we have to use some method to estimate the number of background events in some region and then compare to the actual observed number. So that's where the ABCD method comes in. So it's really the simplest method you could use. There are more complicated extensions, but this is just kind of the simplest case. So the method divides this plane of the two uncorrelated variables into 4 regions based on single cut value in each dimension. And then you get these A, B, C, and D regions. And so I've set these values such that most of the signal ends up in one of the regions. So often it's region A. So here in the top right, this is region A. It has the lowest statistics. Ideally, that means the lowest background, because most of these events with background. So wherever the statistics are lower, that's where the lowest background is. So we want to kind of, in a real analysis, you optimize these cuts to get the best sensitivity, the most signal with the least background. And so as long as X and Y, these two axes, are statistically independent, you can easily show that the number of events in A is approximately equal to the number of events in B times the number of events in C divided by the number of events in D. And so this is only approximation because of finite statistics. In the continuous limit, this would be exactly true. It's saying that this relationship is true for any definitions of the ABCD regions, that any cut values between the regions is equivalent to saying that these variables are uncorrelated. So if the number of events observed in B, C, and D accurately reflect the background, in other words, if these are just background events in B, C, and D and signals only in A, then this formula gives you an unbiased estimator for the number of background events in A. That doesn't rely on looking at region A, so you can keep region A blinded. So if we then take that signal Monte Carlo distribution and look at these cuts on top of that distribution, you can see that while most of the signal events are in region A, there are some that are in regions B, C, and D. So kind of the tails of the signal end up in these control regions, at least in what are control regions in the simplest application of the ABC method, where you just do this number of events in B times number of events in C divided by number of events in D. So because there could be signal events in B, C, and D, if there really is a signal present, then these control regions are contaminated. So this breaks the naive NB and C over ND relationship. So if we tried to use it in a data set where there really was signal present, then you could miss the signal. It would artificially inflate the background estimate in region A, and you could hide the signal. So the more common approach, and the one that's really more correct, is to use the likelihood-based method, where you set up these relationships between, you basically have nuisance parameters that aren't particularly interesting, other than just being able to set limits on or observe the signal. So mu here is the signal strength, and it's just defined to be the number of signal events. Well, the mean, like the expected number of signal events in region A, given some luminosity and real signal cross section. And so then the number of events in the other region is just this efficiency of the region divided by the efficiency, signal efficiency of region A. And so then you can say that the number of background events in all of the regions, so it's normalized. So you have this mu B parameter, the number of background events in A, and then there are these basically ratio parameters, tau B and tau C, which is like a transfer factor between how many more background events there are in region C compared to regions A. And then with this uncorrelation or non-correlation assumption, then the number of background events is D, and D is just the product of these two transfer factors times the normalization. And so with these definitions, then the median number of events in region A really goes back to this definition of the BC over D. And then the total number of events that you observe in any region is just the sum of the end signal and end background. And so for particular values of these parameters like tau B, tau C, mu B, and mu, you can calculate just a Poisson likelihood based on the number of events, and then the expected number of events and observed number of events in each region. And so then you can just, once you have the formula for the likelihood, then you can perform maximum likelihood fit in order to get all the results. And so we can use pyhf for this, and that's where ABCD pyhf comes in. So it's a Python package that does exactly these tests. And so it's really a pretty simple wrapper around pyhf, just giving you some convenience classes and functions to build the proper PDFs and run these hypothesis tests using the likelihood-based ABCD method. So this will show like exactly how I would use it in the analysis. So first you just need to get the number of events in each region. So just these are simple cuts. And then I get this for both the observed events and the signal Monte Carlo. So these are basically the inputs, the yields from data and the yields from the signal Monte Carlo. And then there's uncertainties other than from the statistical uncertainties in the ABCD method. So this is where all the systematic uncertainties would go into. So of course, this is where a lot of complicated studies would go into. And here I'm just boiling it down to say there's just an arbitrary total signal systematic uncertainty of 10%. So this package uses this class that's just ABCD. And so you just give it when you create one of these objects, you just give it the data and Monte Carlo yields, the systematic uncertainties, and then you can form basically all of the kind of standard operations that you can do with pyhf, just using this object that's keeping track of the things that are relevant to the ABCD method. So you can see like the parameter names, these nuisance parameters, and the mu, the signal strength. And then you can do things like a background only fit, just gives you the fit value in the first column for each one of these parameters, and then the uncertainty in the second column. So this is the background only fit where mu is set to 0, so there's no signal, and then you can do a fit looking for the maximum likelihood estimator of the signal strength. So here mu ends up being about 13 plus or minus 9 based on this fit. So it's just like
Mason, I have a question, if you don't mind.
Yeah.
When you talked about the ABCD here, you're running the fit on the counts in each region, ABCD, right?
Yes.
But you're not like the likelihood fit isn't trying to optimize where you would draw those regions or anything.
Optimize what?
The likelihood fit isn't trying to like optimize or change how you draw those regions.
No, it doesn't. It doesn't change the observed number of events or in the number of events that fall in the different regions for signal. It's only changing these parameters here. So it's really just the fit to you're given some observed number of events and distribution of signal into those regions, and you're just fitting these parameters to that distribution.
Okay.
Yeah, so that would be another step. That's something that I would like to, and that wouldn't go. It's not something for this package. I would say I'm trying to keep things modular, but that's something that I try to do then at a higher level in my analysis, optimizing the actual ABCD region boundaries. But this is just doing the hypothesis test.
I also have a question. When you set up the model here, you hand over the signal uncertainty float. Can that be anything more complicated, like multiple components or like region or phase space specific?
So this is something this is the main like request that people have wanted to do, because for at least for the previous iteration of my analysis, we just had this one value that was the systematic uncertainty for the signal yield in region A. So we use it for all of the regions. But one of the things that I've been working on is extending it so that you can have a more complicated thing. So you can have uncertainties where the events can migrate between the different regions. Yeah, exactly. This is something that I'm working on. And that's something that's important for being able to apply this to more analyses. the main place for it, that's the bottleneck is yeah, exactly that, being able to have more complicated systematics. Okay, let's see, and then there's just a few more things on here. So just some other convenience functions, so you can get the likelihood from these fits. So here it just gives you all the mu values and then the twice negative log likelihood values. So you can plot that. So this is what the likelihood looks like. So you can see here the minimum is that 13, the plus or minus 9 here. And so because this is just a toy example, I know exactly how many signal events there really are in this like observed data set, and it's around I believe it's 10. So you can see, so basically the true underlying signal strength is 10, so well within this fit uncertainty here. And so you can see that we can exclude very high values of the signal strength, can exclude a signal strength of 0. It's not, it's still within the fit here. So we can't exclude exactly exclude the signal-free hypothesis, the background only hypothesis. So we are just setting, in this case, we just set an upper limit on the signal strength. And then so you can get some of the standard like CLB and CLS plus B, these things that they come straight out of pyhf that are used in the CLS method. So that's just the mu values and then the CL values. And then for CLS, you get, again, just like pyhf, you get so first of the mu values, and then you have the observed CLS values, and then the expected bands. So you get a few arrays here, which are the median, the expected CLS values, and then plus or minus 1 or 2 sigma from this. So that's what this third array is. You just get 5 different arrays of these -2 sigma, -1 sigma, the nominal, and +1 sigma, +2 sigma. And then you can, a lot more easily see this in like a Brazil band plot like this that we usually see, where it plots the observed and expected CLS values and these bands of uncertainty. And so you can see that the observed upper limit is up here around 30. The expected is like 19 or something. So this observed is there's a bit of an excess, is between 1 and 2 sigma, but not enough of an excess. There's no discovery in this case, but there's at least you can set the upper limit. And as the statistics increase in this particular case, because I know that there's an underlying signal here, this observed value, you get further and further away from the expected bands, and then you would start looking at potentially a discovery. So because there's not a significant enough excess, you would set an upper limit. And so this just gives you the observed, so the point where these lines cross the alpha of 0.05. So the observed upper limit is this about 30, 29.8, and then you have the bands of the expected upper limits, where the median is about 19. And so you can see it's this 30 value is between the 1 sigma and the 2 sigma values for the expected upper limits. Okay, so that's just a little toy example that shows how this package works. So the ABC method, one of the most common methods, certainly within the Atlas Exotics group for background estimation. It's really a family of a lot of different techniques. Like when it gets more complicated, people often call it the matrix method. It's basically the same technique, just with more regions. And pretty much all analyses are, unless they have very good separation between, like very stark separation between signal and background, you're usually using a likelihood-based method. And so this ABC pyhf, it's small, it's a purely Python package. It doesn't have a lot of dependencies, pretty much just pyhf. It doesn't have any dependence on experiment-specific formats or code, so this is public on GitHub, even though I apply it to my Atlas analysis, so I know that it works out of the box for most simple cases, where, like I said, I'm using in my analysis, and a few others are using or are trying out this package, at least within the Atlas Exotics group. And one of the main things I'm working on right now is that this is intended to be extensible to accommodate more complicated use cases where you have more complicated systematics, like I said, migration between the regions, and so per region systematic uncertainties, or where you have multiple ABCD planes that are that have parameters in common. So these are things that I'm working on right now. And I have some links to the repository and the PyPy package and some of my other presentations. And yeah, I think that's a few minutes for questions.
Yeah, nice. Thanks very much, Mason. That was a great talk. So we do have time for questions. So I'm first going to go to Zoom. So if people on Zoom have any questions, please just raise your hand. So all right, I don't see any hands raised on Zoom, but I'll still keep a lookout. But I see that Jordan has his hand raised in the room.
So you've shown the upper limits here using the ABCD pyhf package. What do you get if you do it the sort of naive way? How does that compare?
That's a good
Because
question.
I guess the goal of this is you get a yield for A, right? You get a yield for the signal in A because, or a background in A because you're estimating the background. So how does what you get with ABCD pyhf here compare to sort of the naive approach?
Yeah, let's see. I don't know off the top of my head what like the expected limits are. I mean, I guess what I could do is I could look at these. Yeah, I could try. Let's see, like B. I could try just this B times C over D, and that would at least say what the. So this would, if you just did this naive method, so like, in other words, like the expected number of events before, like the pre-unblinding expected number of events would be like 23. So we would compare that to the observed number of events of 33. So then that, you know, you'd have to do the Poisson uncertainties, but I guess, yeah, that's a little, it's a bit high. It's but another point is, so I mentioned how, you know, if you don't do the likelihood-based method, then you could miss a signal because you inflate your background estimation because you're not doing the simultaneous space of signal and background. And so basically, if you tried to do this method, maybe you wouldn't. Yeah, I guess your upper limit would be different. Basically, it would be wrong because you're not taking into account the fact that there could be signal there. So I don't know exactly what the difference would be.
Yeah,
you would set upper limits that would, you know, be not technically correct because you're not taking into account the fact that there's could be signal events in here. So it's a matter of, you know, it's not correct because you know that there could be signal events in these other regions.
Yeah, I guess what I'm wondering is because I know we have used a naive approach in the past, and I guess we put a much more conservative uncertainty on whatever comes out of that. By using a likelihood-based approach, you could probably say that you can get a smaller uncertainty on that number compared to the naive approach.
But Jordan, when you say that we've used this in the past, like, are you talking about an Atlas-SUSY analysis or what in particular?
SUSY and Exotics have used a non-likelihood-based approach for ABCD. Even in standard model for Atlas, the default is actually to use a regular non-likelihood-based approach for estimating things.
Okay. All right, so I don't see any hands on Zoom, and there's a question behind us.
So you have shown the XY plot this one. So
I copy text up.
suppose I take it off the whole layer of some like HCAM or UCAM, and there are more than one these signal type of things. So can you work upon those with this ABCD? Like how will you divide the whole thing into each?
Oh, so normally, yeah, it's interesting. So normally these variables are already, you expect them to be along an axis that's a discriminant. The discriminants between signal and background. So you want signal to have some distribution that's peaked different in a different place from background, and then you put the region boundary between those those peaks in the distribution. I don't know if it would work for like calorimeter images because I don't know if there's like a 1D discriminant that would separate signal and background. So more likely what you would do is you would train some machine learning method, like this is what I do. I use a neural network for both of the axes. So they're both discriminants and you just need to make sure that they're uncorrelated, and then you apply it to that. So it doesn't necessarily have to be like a direct like variable that you get out of the detector. It can be some function of all of the energy deposits and tracks and things.
Okay. Yeah, the time for I think one more, and then we probably need to move on.
So for this method to work, does X and Y have to be uncorrelated for both signal and background, or will only background work?
Yeah, only background. Yeah, and that's so it's just based on it doesn't matter if it's correlated in signal or not, because you know what the distribution of signal events is, assuming your Monte Carlo is good for signal. We assume we can simulate it well, and then whatever we parameterize, whatever we can't simulate well in the systematic uncertainty. For data, this is really the important, this assumption of like the number of background events in D is the product of these two nuisance parameters, basically, because you rely on these being uncorrelated in order to be able to get an estimate of background events in A without blinding region A, or without using information from region A until you do the simultaneous fit.